Good morning, everyone. I am V. Vignesh, ME Power System Engineering from Tyagaraja Engineering College. I am going to present my project, which is the topic is the analysis of power quality issues in electric arc furnaces under the guidance of Dr. V. Suresh Kumar, Professor in the Department of Triple E. Let's go to project. This is my presentation overview. In the presentation, we are going to discuss about the introduction, problem identification, problem formulation, the literature review, and the research gap identification, and then the proposed implementation, and we have to going to see about the MATLAB Simulink results. In general, the electric arc furnace, which is mostly utilized in steel industries for melting the scrap metal to form the metal formation in industry, is done by many other technology methods. One of them is the electric arc furnace technology, and some other methods are blast arc furnace technology and induction furnace technology. uh, but in condition, we are going to deal about only the electric arc furnace technology, because the electric arc furnace is considered as a dirty load in the power system network due to its non-linear behavior, and it produces severe power quality issues in the grid. This is the work that we have done in phase 1 of the project. In phase 1, we have considered an utility side, only about an industry side, how an electric arc furnace, in the general, the electric arc furnace is fed by two types of supply. One is about in general, the conventional AC one, and the DC electric for supply. In phase 1, we have considered a DC electric arc furnace, which is fed by a thyristorized converter. In and we have analyzed the power quality issues such as voltage THT and current THT at the point of common coupling PCC, where the electric arc furnace is connected at the utility point of view. For feeding a DC supply to the DC electric arc furnace, we have tested two types of topology. One, the conventional thyristor based rectification topology for both 6 pulse and 12 pulse, and the IGBT based rectification topology for both 6 pulse and 12 pulse. And also we have analyzed the active power and reactive power variations, and also the power factor at both the load side and the supply side, and all the parameters are verified with the power quality standards by IEEE 519 1992 standards. The problem identification is, mm, when interfacing the electric arc furnace in the grid, it will pollute the customers who are connected at the utility. So we have it produces some power quality issues such as harmonics, flicker, and voltage sag and swell due to large reactive power variations, and during the boring and melting process, it produces more current harmonics. So to mitigate this power quality issues, we have to install some fax devices such as STATCOM, SVC, static power compensator, and passive filters and active filters, but it is very costly and not economical. And due to the load varying nature of arc furnace, the predictability of harmonics is uncertain. It varies due to the loading of scrap metals in the furnace industry. And the problem formulation, we have developed two models. The first one is the AC arc furnace model using hyperbolic EAF method, and the DC arc furnace model using Casey-Meyer arc furnace equation theory. We analyze the grid in different cases without electric arc furnace load, that is without any non-linear load, and with AC arc furnace load, and with DC arc furnace. We have studied three cases, and the power quality parameters are measured and validated. In the literature review, there were many literature review carried out, and how the power quality has been power quality has been mitigated, and how the power quality has been improved, and how the model has been validated, and how the model has been developed, carried out in several literature, and how the SVC mitigates the power quality issues in the grid. These are carried out, and these are the literature review and the research gap in various literature papers and IEEE papers. We have identified that there were no such kind of test project has been carried out in power system network, that when arc furnace is present in the tested IEEE bus, IEEE 33 bus system, and IEEE 9 bus system, and a standard IEEE system, how the power quality has been affected due to the penetration of nonlinear load in the grid has been identified. This is the AC electric arc furnace model. Here I is the arc current and L is the arc length, and V80 is the arc furnace operating condition voltage, and A, B, and C, D are the parameter constants which predict the model nature of the arc furnace, that is the non-linear nature. And this is the MATLAB modeling of arc furnace, AC arc furnace. The equation is modeled for three phase, and it is coded in a MATLAB embedded function. And this is the VI characteristics of AC arc furnace, which is a non-linear nature behavior, and the x-axis is the current, and the y-axis is the voltage. And in the proposed implementation, we have to first implemented the IEEE 9 bus system, and IEEE 15 bus system, and IEEE 33 bus system. This is the schematic diagram of the IEEE 9 bus system. Here there were 3 loads and 3 transformers and 3 generator bus. This is always called as 3 machine bus system. And here these are the line parameters of IEEE 9 bus system. This is the MATLAB simulating diagram of IEEE 9 bus system. Here we can see the transformers and 3 kinds of load, which all the 3 loads are linear loads, not a non-linear load. During that the FFT analysis of that PCC, due to linear load, there were no power quality issues in the grid. The voltage THT and current THT is 0%, but in real time there will be some amount of little amount of little amount of THT will be present, but in MATLAB there will be a steady state case. So for linear load, it produces it indicates only the 0 THT. These are the phase B and phase C. For 3 phases, the voltage THT were measured. This is the current THT for phase A, phase B, phase C. Next, the second case is the grid with the AC arc furnace. Here in bus 8, we have placed the AC arc furnace, and we measure the power quality parameters such as voltage THT and current THT at bus 8, and the adjacent bus such as bus 6, how it affects the adjacent buses when an AC arc furnace is connected at a load. So we have taken the measurement at two different buses. The first bus is where the arc furnace is placed, and the second bus is the adjacent bus with reference to the arc furnace bus. This is the voltage THT. In this we have seen that there are several order harmonics were present, but there were little amount. The voltage THT is on about 0.42% at phase A. This is about phase B, about phase C, and this is the current THT, which is more than 64.85%. Percent, which is a higher percent as per according to TNEB standards. The current THT should be at limit of amount only about 8% only, but it is about 64.85%. Is this for phase B? This is for phase C. It is the adjacent bus which is measured voltage CST 0.1%. It will be a little amount because the transmission line modeled is as a capacitance nominal pi model. In nominal pi model there will be two shunt admittance, which is a capacitance parallelly connected, which is shunt connected capacitance, and this is the current TST, which is about 4%, and it is another phase 5%, another 1.88%. You can see the how much order of harmonics were present. The order and even order harmonics all are present. We cannot predict which order of harmonics will present in the grid. When grid with DC arc furnace, then we are going to validate the grid with DC arc furnace. First, we are going to implement the conventional topology, thyristor based topology, which is a 6 pulse converter topology. During 6 pulse, the voltage THT at bus 5. In DC arc furnace, we are going to place the DC arc furnace at the bus 5, and the voltage THT is about 11.05% for all the phases, and the current THT is about 34% around. This is the bus 8. You can see the results. This is the 12 pulse thyristor based configuration. Next, the beauty of the DC arc furnace technology is when we fed with the DC converter supply, we can easily predict the harmonics nature, because during 6 pulse we can calculate the harmonics such as 6p plus or minus 1, fifth order, and third order or seventh order. So that like kind of harmonics will be present. For that we can easily install the SVC or passive filters for the required amount of order harmonics. When we install 12 pulse, we can get a 13th order harmonics, 13th order or 15th order or 11th order. That type of odd harmonics were present. For that we can easily install a passive filter like or SVC for mitigate the power quality issues. When we compare to AC arc furnace, we can't predict the nature of harmonics, so we can easily go for a DC arc furnace. And also for a DC arc furnace, the electrode consumption for arc furnace is low, because in DC arc furnace there will be only one electrode. For an AC arc furnace, for 3 phase we have to install 3 electrodes. And here the voltage THT at bus 8 and current THT at bus 8 for 12 bus thyristor based configuration. When implementing the IGBT based arc furnace, for IGBT based topology we are going to implement a gate pulse. For gate pulse we are going to install the DQ based transformation for DQ access theory. In DQ access theory, it is called as a voltage oriented control method. In IGBT based arc furnace, the voltage THT for 6 pulse voltage THT is 0.11% and 0.008%, and the current THT is sufficiently reduced at bus 1.5% within the limit as per TNEB standard. And at bus 8, for bus 5 about 1.1, then bus 8 it will be normally reduced due to the capacitance effect between the lines and the transmission line, the length. In the transmission line we have fixed length about kilometer of 20 kilometers. So about 20 kilometers there will be amount of harmonics will be eaten by the line. So this is the current THT at bus 8 from the inference. That's all about. From the inference it says that this is the IEEE 9 bus system DC arc furnace. You can see that IGBT based chopper 12 pulse. 12 pulse, the current THT and the voltage THT were significantly reduced, but it doesn't need any SVC or fax devices for mitigating the power quality issues. This is the IEEE 9 bus system with the AC arc furnace. The current THT were very high, but at bus 8 it will be a significant amount. For one disadvantage is in the AC arc furnace we can't predict the nature of harmonics. For IEEE 15 bus system, for an IEEE 15 bus system which is a radial distribution system, we have placed a DG which were feeding the additional loads, which are feeding power to the additional loads. For that we have placed arc furnace at bus 1. When implementing 6 pulse topology, 6 pulse at bus 1 and bus DG, there were mitigating harmonics. The harmonics were present, and the harmonics also affects the DG. The same condition for AC arc furnace. IEEE 33 bus system with the DCAF. Conclusion. On the conclusion, it is said that the AC arc furnace, which is more vulnerable to the grid, and even we install SVC or any fax devices, we can predict the nature of harmonics. What kind of harmonics what order of harmonics should affect the grid. So when we go to the DC arc furnace technology, the DCAF topology, when implementing 6 pulse thyristor based topology and 6 pulse IGBT based topology, and comparing to both the thyristor and IGBT based technology, the IGBT based topology is well known for arc furnace, DC arc furnace DC arc furnace technology, because it does not pollute the grid. We can verify it in the results that we have shown. So for smelting applications, the IGBT based DC arc furnace technology is well suitable for smelting applications. That I conclude. Thank you.